Good morning. We want to get started with the Bjerknes Memorial Lecture, and I'm glad to welcome you this morning. I'm Ann Thompson. I'm the president of the Atmospheric Sciences section of AGU, which sponsors this lecture every year, and I want to introduce my co-chair, co-convener for the session, Peter Webster, who's the president-elect of our section. Before I introduce the speaker, I want to mention, and I'm easily reminded because I'm being blinded by the lights, that this lecture and the Charney, which will follow at 9 o'clock for the first time, thanks to AGU, are being videotaped. So if, like me, you have to leave prematurely to give your own talk, or your colleagues couldn't be here, or you want to share it with your coworkers and students, because these are really top-flight lectures, you'll be able to download the video from the AGU website. So I want to tell you a little bit about our speaker, Dr. Paul Newman of NASA Goddard Space Flight Center. He's one of my longtime colleagues and best friends in the ozone world. We both went to NASA Goddard in 1984. But first, Dr. Newman always wants you to know he's a Seattle native and a graduate of Seattle University in physics. When he came to Goddard in 1984, he was a freshly minted physics PhD from Iowa State University. And 1984 was the year before the Antarctic ozone hole was discovered. So he's a very fitting speaker because his career has paralleled a fascinating journey through measurements and modeling of this phenomenon, which is his topic this morning. So he's written among his 150 peer-reviewed papers, most in AGU journals, a series on this year's Antarctic ozone hole. So you can go and read about the variability in his record. He has also led 19 field missions to study the chemistry and dynamics associated with stratospheric ozone depletion. And he has contributed as well to the development of coupled chemical dynamical climate models at NASA Goddard. So it is not surprising that he was asked 5 years ago with his co-authors here, and as an aside, I want to say John Piles, one of our new AGU fellows this year, he was asked with these folks to co-chair the scientific assessment panel that reports every 4 years to the Montreal Protocol. I'd just like to mention a few of his accolades along the way. The Arthur S. Fleming Award, which is in recognition of great achievement and service by U.S. government employees. The Pecora Award with the Tom Science Team for satellite remote sensing. Ozone Watch and Protector Awards from both NASA and the EPA. And the highest Earth Science Award of NASA Goddard, which is the William Nordberg Medal. He also is an AGU Fellow and has just been elected a Fellow of the American Meteorological Society. So join me, please, in welcoming Dr. Paul Newman.
Thank you, Ann, and good morning, all. I'll just remind you to mute your cell phones so that you won't wake up your colleagues sleeping next to you. I'm going to start off by talking a little bit about my co-authors here. These are the four co-chairs of the Scientific Assessment Panel for the Montreal Protocol. Professor Ayite-Lo Ajavan from the University of Togo, John Pyle from Cambridge, and Ravi Shankara from NOAA. I will say that every 4 years we form the assessment panel, and I can't even begin to spell out all the people that contributed to the 2010 assessment. Just I put the numbers down here amongst the authors, co-authors, contributors, reviewers. There were 312 scientists from 39 countries that contributed to the scientific assessment. So ozone just seems to not want to leave us alone. March 2011, there was an announcement that there was severe ozone depletion over the Arctic. And in fact, these are just headlines. I grabbed a few off of the web here. So it appears that things are getting worse in the ozone layer. That was followed just a couple of weeks later that Antarctic ozone is getting better. And that was, again, I grabbed all these headlines off of the web. So what's actually going on? Are things getting worse? Are things getting better? So I'll try to clear the air a little bit, so to speak, about what's actually going on with ozone. And I'm going to use the assessment to actually cover all this material. So I'm going to start off with just a little historic background. And the first thing I'm going to point out is way back in 1974, Rich Stolarski and Ralph Cicerone in the Canadian Journal of Chemistry published a paper indicating that chlorine atoms can catalytically destroy ozone. So a chlorine atom will destroy an ozone molecule and then reform itself. And you find that one chlorine atom can destroy, roughly a thousand or so, a few thousand ozone molecules. So chlorine is a pretty powerful ozone depleter. Now that was followed shortly after that by the paper by Mario Molina and Sherry Rowland, in which the stratospheric sink for chlorofluoromethanes, and they showed that CFCs are accumulating in our atmosphere, and their primary sink is photolysis in the upper stratosphere, where they release this chlorine, which can then catalytically attack ozone. So these two papers really show, or saying that, in fact, we could have large ozone losses if you just let CFCs increase uncontrollably. Now, I will point out for all of you young scientists that you don't have to, both Mario and Sherry won the Nobel Prize in 1995, and for you young scientists, you don't have to be perfect to get a Nobel Prize. If you notice the title here, you see atom C, it should say atom catalyzed. You don't have to be perfect. Okay, so here's the basic storyline. Chlorofluorocarbons, the accumulation of them leads to ozone loss, which then leads to increased UV. So what I'm going to say is just a brief word about what are chlorofluorocarbons. And I'm actually going to include halons in this group here. They're used as solvents for electronics. They were used as foam blowing agents for plastic cups and so forth. They're used in asthmatic metered dose inhalers. They were used as aerosol propellants. For many of us growing up in the 70s, we all remember the ban of hairsprays and so forth. They're used in car air conditioners. They're used in refrigerators for both the insulation and for the carrier gas. They're used in air conditioners, home air conditioners, and mobile air conditioners. And halons are used in fire extinguishers. So these gases have a wide variety of purposes. The unfortunate aspect is, of course, they lead to ozone loss. Now, what I'm going to do, just in the way of motivation, I'm going to skip forward to increases in ultraviolet radiation, just as a motivator. And this is from there are three panels to the Montreal Protocol. There's the Technology and Economics Assessment Panel, the Scientific Assessment Panel that I'm on, and then there is the Environmental Effects Panel. And this is the report of the Environmental Effects Panel. And you can see I've listed out a few things that UV does. UVB leads to increased levels of sunburn and skin cancer. In fact, I've listed the three basic kinds of skin cancer: melanoma, which is the most lethal, squamous and basal, which are much more treatable if caught early. Just as an indicator, if in the U.S. an American who lives to the age of 65, 4 to 5 out of every 10 Americans will get either a squamous or a basal in their lifetime. And 90% of those cancers are related to your cumulative solar exposure. There are eye cancers, there are UV-induced allergic reactions. In fact, I'm surprised. I've met a lot of people who get these UV allergic reactions. It's a surprising number of people. Infectious diseases. One positive benefit of UV is it increases your vitamin D, which is necessary for bone health and so forth. Food security. One thing I've come to really appreciate about UV radiation is the impact on crops. And of course, if UV got to very high levels, that would have an extreme impact on crops. And finally, there's degradation of dissolved organics and degradation of materials also. I think a lot of us remember how our windshields, the dashboards would crack from the plastic in the dashboard with time, and that came from UV radiation. Now, just again, another little motivator here. Why is ozone a critical atmospheric gas? This is some work I did with Georgi Georgiev, Matt Kowalewski, Scott Jans, and myself. And what we did is we wanted to find out what would happen if you had no ozone layer. And our little victim here is a little basil plant here. And this is a solar simulator here. So you can see the beam there. And we had a little camera here that we took time-lapse photography of. So this is a little bit melodramatic, but it's an illustration of what happens to a living thing if you expose it to UV. So this is a little film, and it's time-lapse every 10 minutes, and it goes for 4 days. And this is the first shot in the film. So you see, as you go through the film, you'll see it suddenly change color because we exposed the plant for a total of 27 hours, and then we turned off the lamp and then just watched it for an additional 3 days. Now, hopefully this will play. Whoops, nope. Oh, I'm having problems. Here we go. Okay, so here's the start. You can see there's a rapid impact on the plant. You can see it turning brown, and then that's where the lamp goes off. And then we just let the plant sit there for another 3 days. We kept it watered. We checked heat levels and ozone levels in situ in the plant, and there wasn't high ozone levels. We aspirated the plant a little bit. It did heat up a bit, but not too bad. We pulled the plant out, and unfortunately, you build up these toxins in the leaves. The plant died within a few days. It was completely dead. You can kind of see back here where, because the camera is a little bit offset, you can see places where you weren't getting direct exposure to UV, and the leaves appear to be fine. But in fact, the plant did not survive. So that's just an illustration. It's a little bit melodramatic, but I think it indicates the point of why you need an ozone layer. Okay. Now I'm going to jump a little forward and talk a little bit about the Vienna Convention, the Montreal Protocol, and the assessment. And these people confuse the Vienna Convention and the Montreal Protocol fairly often. So let me just say what they are. The Vienna Convention for the Protection of the Ozone Layer, it's a multilateral, that is, a multiple country agreement. And it's a framework effort to protect the ozone layer. It has no binding actions associated with it. But this is the agreement that all the countries, every country in the world has signed the Vienna Convention, including the newest country, South Sudan. It recognized the need to protect the ozone layer. It established a secretariat under UNEP and regular meetings for ozone layer issues, and established a framework for scientific research. So all the science that we do as part of the Montreal Protocol is actually mandated under this agreement. Now, the Montreal Protocol is an agreement that supplements the Vienna Convention. So this agreement here falls under the Vienna Convention. And it has a few really key aspects to it. First of all, it regulates the production and consumption of specific substances. So it doesn't try to regulate the effluent, that is the waste gas, like you might do with carbon dioxide or methane. It actually regulates the production and the consumption within countries. It has a multilateral fund. This is a fund that is supplemented every 3 years, and it's used to fund projects in developing countries to eliminate ozone-depleting substances, also fund some education, a number of things that it does to enable developing countries to eliminate CFCs and other ozone-depleting substances. And finally, it establishes an assessment process under Article 6. So every 4 years, the Scientific Assessment Panel is mandated to supply a report to the Montreal Protocol. So that's just the difference between the two agreements. Now, this is a meeting that was held in Doha, Qatar in 2009. And you can see every country has a few seats, and they'll have a little sign in front of them. Sometimes they have little flags. This is the ozone secretary here in charge of the secretariat, Marco Gonzalez. This is Martin Sioris, the delegate from Canada. The delegates choose from amongst themselves who will be the chairman for the Montreal Protocol meetings. This is the American delegate. This is Dan Reif-Snyder, who is the Undersecretary for Environment. And way in the back here, down at the bottom, back of the bus, here are where the scientists sit. And the other interesting thing is notice that all these seats around us are empty. Something about taking showers, I don't know. Okay, so now these are the assessments that we've had in the past. So these assessments here, the WMO stratosphere, these three were done under the auspices of the WMO. These are the assessments that came under the Montreal Protocol, and occasionally this is a joint assessment between the IPCC Working Group 1 and the Technology and Economic Assessment Panel. So you can see we've had 7 assessments now. The 2010 assessment is our latest assessment. So this was just released at the end of last year, and it is publicly available over the web. I can supply, if you want to get a copy of it, you can ask me and I can try to get you one. Okay, these are the authors. Again, I already talked about the co-chairs. Chris Ennis is our coordinator editor. I really want to thank Malcolm Coe, Ted Shepard, and Susan Solomon. They kind of served as an executive review committee for us and helped really with establishing the full outline for us. There's also, here's the chapters that were in the assessment. Steve Monska and Stefan Riemann did chapter 1 on ozone depleting substances. Ann Douglas from Goddard and Vitaly Fyolatov from Environment Canada. I hope that continues in the future. We're in charge of stratospheric ozone and surface ultraviolet radiation. Slimane Becky from France and Greg Boddicker from New Zealand, future ozone. And Piers Forrester, Dave Thompson, stratospheric changes in climate, which is the new chapter we added. John Daniel and Gus Velders, a focus on information options for policymakers. And then finally, David Fahey and Michaela Hagelin did the 20 questions and answers. And this 20 questions and answers is really a wonderful summary of the science. You could read it in an evening, a couple of hours. You can read through this whole 20 questions and answers, and it's really a great summary of ozone science. So I want to go through the key findings of the assessment. I'm going to start off by pointing out that ODSs are declining as we expect. This is red line, kind of shows the observations, and it's a little bit cartoonish here just to have a very simple point. They increased. The Montreal Protocol has now led to a decrease, and we expect them to continue to decrease into the future. Carbon dioxide continues to go up, and we now know that climate change and the ozone layer are intricately coupled. I'll show a couple of other view graphs on that. And as ODSs disappear in our atmosphere, climate gases will become more and more important in controlling the changes of the ozone layer. The Antarctic ozone hole, it continues to persist. It's still with us. It's expected to recover sometime later this century. The northern mid-latitude ozone, and in fact global ozone, is smaller than the ozone hole, much smaller than the ozone hole, and it's not gotten any worse because of the Montreal Protocol. And sometime in the middle of this century we ought to see recovery. And finally, UV radiation. We never really got to these extreme depletions, with the exception of kind of down over Antarctica, to really impact humans. And so there's only been small increases in UV radiation. Okay, so those are kind of the big findings. I'm going to go through those in a bit of detail now. Okay, let me start off, go back to CFCs again, chlorofluorocarbons and other ozone depleting substances. And so these are the principal findings that have come out. As I said, the abundances are continuing to decline. Total chlorine continues to decline in both the lower atmosphere from surface observations, and then when you look from satellite at the upper stratosphere, you can see levels of HCl are going down. So you get both a satellite confirmation and a ground observation measurements that indicate chlorine's going down, which is great news. CFCs, not methylchloroform, are now contributing most of the chlorine decline. Methylchloroform has a short lifetime of about 5 years, and so it's gone down fairly fast. So now most of the methylchloroform has gone out of the atmosphere. That was what was causing most of this decline early on. So now we're left with just the CFC. Since methylchloroform is largely gone, CFCs have longer lifetimes, so the recovery rate will slow down a little bit. Total bromine. I haven't mentioned much about bromine. Bromine is a very efficient ozone-depleting gas, and bromine is also declining now. We see in the surface observations that bromine is now going down. And actually the halons are, this is just kind of a sub-bullet here, but halons are decreasing. And then finally, I'm going to get into a little bit about HFCs and HCFCs. Now, HCFCs are interim compounds, and HFCs are not ozone-depleting substances, but they're both growing considerably. And I'll get into that last point in some detail in a minute. So this is a timeline, and this is in the emissions in megatons per year. This is from the Gus Velder's paper and is in Chapter 5. You can see that these are the emissions up to about 1990 or so. You can see the impact of Mario Molina and Sherry's paper here in the mid-70s. And in fact, the emission rates didn't go up for a few years. Okay? But then they began to pick up again as people began to use them more in air conditioning and so forth. And so this was the projected growth of CFCs in our atmosphere. Now, I'll come back to talk about this particular line here, this growing CFC, and what that does to the ozone layer later on in the talk. Well, the Montreal Protocol had a significant impact on this. The Montreal Protocol was negotiated here in 1987, and the emissions began to fall off. HCFCs, these are an interim replacement, they began to grow, and in fact you can see there's a little, they were starting to increase. HCFCs were actually regulated in the 2007 Montreal meeting, and so they established guidelines for reducing the production and consumption of HCFCs, so they'll also go down. Now both of these are ozone depleting substances, and you can kind of get a, we're about something up here around peak of about 1.5 megatons per year of these compounds. Now, what are they now using as, or going to be using as refrigerants? These are the HFCs, okay? And this shows the growth in HFCs. In fact, we kind of hit a minimum here, and it's going to start rapidly going up. And this is because not only are we replacing the CFCs and the HCFCs, but developing countries are starting to buy refrigerators and air conditioners in very large volumes. And so the total amount of these refrigerant gases and foam blowing and other purposes is going to go up with time. And in fact, sometime around 2050 or so, it'll be out here at about 3.5 megatons per year. So the usage of refrigerants isn't going down. Now, this has some implications, and I'll get into that in a little while. So the main point here is that we started off with CFCs. Those were regulated here in 1987. We used a transitional compound, HCFCs, which are less ozone depleting. Their ozone depletion potentials are smaller, so they have less impact on the ozone layer. And that's going to transition to these hydrofluorocarbons, HFCs, and they'll go up quite a bit with time. These are some of the actual observations. This is a slide provided by Jim Elkins. And on the top, you can see two gases, CFC11 and CFC12. On the bottom, you can see methylchloroform here, CFC113, and carbon tetrachloride. Now you can see that all of these gases are now declining. The lifetime of CFC12 is about 100 years. He has various stations here from Alaska down to the South Pole. You can see that the Alaska, Colorado stations, they had the highest amount, and then a few years later, you saw that same concentration get down to the South Pole. So this indicates the time it takes for material to be mixed from the northern hemisphere into the southern hemisphere. And you see that after the agreement that in fact the global concentration has kind of tightened up. So the levels of CFC11 or CFC12 everywhere are about the same now. And they're going to be, you can see that finally you can see the decline right here. As I mentioned, methylchloroform has a short lifetime. It's going away fast. If you take all these things and total them up, that's where you get your total ozone depleting substances. So you can now see that things are going down. Just as a point, the Vienna Convention here was signed in 1985. The Montreal Protocol signed in 1987. You can see shortly after that things begin to turn over. And then there's been subsequent amendments that have strengthened the Montreal Protocol. That's one thing I skipped over, is that the Montreal Protocol is an organic protocol in that it can supplement itself and increase the strength of the regulations with time. And so they've done that over the years. And as I mentioned, HCFCs were regulated in 2007, and that's where that happened there. Okay, now I'm going to talk a little bit about carbon tet. Carbon tet is basically used as a feed gas to produce things like CFCs and HCFCs. And these are from two measurement groups, the Ale Gauge group and the NOAA group. The black line in the middle here is from the 2006 assessment. That's the average and then the projection forward of what would happen to carbon tet. So you can see it's continuing to decrease in the atmosphere. Now let me say something about emissions of carbon tetrachloride, because this is where the mystery comes in. There's two ways of getting at emissions. You can get all the countries to report what they're producing and consuming. That's this black line down here. Some uncertainty in that, so there's a couple black lines there. So that's what the reported emissions are from all the countries. Now, if you look at the equation for the concentration, global concentration, you have the time tendency here, you have emissions, and then you have losses. And I'm just going to consider the losses. It's just a linear process, and that works out pretty well. And this is the lifetime. And you can estimate the emissions just by taking the observations and knowing a lifetime. You can calculate emissions. And this red line is the top-down estimate. So it's taking the observations and estimating it. And you can see that there's a big difference between the atmospheric top-down estimate and the estimates from what the countries are reporting as their emissions. So carbon tet, and you can actually see here, when we projected forward carbon tet, we expected it to go down much faster than it actually did. It isn't going down that fast because somewhere there's either greater emissions or we have an error in that lifetime. Now the blue lines here actually show the errors, and if you choose a couple of some wild estimates on the lifetime. So it's actually not this term. It's got to be this emissions term. We don't understand the emissions of carbon tet. And the discrepancy is about 40 gigagrams per year. So it's a pretty big source of carbon tetrachloride in our atmosphere we just don't understand. And I just listed out the things that possibly could explain this. It can't be explained by the lifetime. It could be errors in reporting, deliberate errors by, you could have deliberate errors. Countries just don't want to report what they're actually using or producing. You could have errors in the analysis of the reported data. I think as scientists we always have to admit we might be making mistakes. There could be possible illegal production, unknown sources. A lot of people are arguing there may be unknown sources of carbon tet, or poorly estimated sinks. That's something that scientifically we have to take a close look at. Okay, so just an illustration that we don't know everything about ozone and ozone depleting gases here. HCFCs, now these were the interim compounds. They're the transition compounds. They have lower ozone depletion potentials than chlorofluorocarbons. They're all continuing to go up right now. So these are observations you can see there through 2009. And then again the same two networks, AL Gauge and the NOAA networks. So you can see these three compounds, 22, 142b, and 141b, are all continuing to go up. They're controlled at 2007. And you can see for the phase out, developing countries are going to do this. It's rapidly increasing again because more people are using air conditioners and so forth. But production is frozen. Developed countries, 95% reduction, full phase out by 2030. So we expect these compounds to eventually turn over. HFCs, there were the replacement compounds, and they are all going up rapidly. This is a logarithmic scale over here, time, and so you can see this large, all these HFCs, the hydrofluorocarbons, which have no ozone depletion potential, they're all going up. Okay, so now what I want to do is again give you a little bit of contrast. I've mentioned that the Montreal Protocol, CFCs are powerful greenhouse gases. So CFCs, actually the regulation of CFCs was important for climate. And just to give you a scale, this is from Gus Velder's paper. It's figure 5.6 in the assessment document. You can see this is CO2 emissions here, and here's the IPCC SRES range. You can see that this is the CFC equivalent in gigatons of CO2, and you can see that was going up, and again, here's the projection. You can see it was going up rapidly. Now, the regulation of the Montreal Protocol brought that down, in fact, very considerably. You can see here's the CFC halons and others, contribution in gigatons of CO2 equivalent, and here's the HCFC contribution. Okay, so the Montreal Protocol has done quite a bit for climate, as well as ozone depletion. In fact, you can see this is just the emission reduction of the first Kyoto Protocol commitment period, and it's actually pretty small compared to what the Montreal Protocol has done, about a factor of 5 in difference. Now this is what will happen as HFCs grow. HFCs have global warming potentials, they have relatively long lifetimes, and so the growth of HFCs as refrigerants and foam blowing agents and so forth, that will eliminate a lot of the gains made by the Montreal Protocol as a climate treaty if these compounds are not regulated. They may be regulated under the Montreal Protocol eventually, but they're not there yet. I should also mention they are in the Kyoto basket of gases, so it is potential that under the UNFCCC, one day these HFCs might also be regulated. Okay, so I'm kind of done talking with CFCs. Let me talk a little bit about ozone loss. The ozone hole that occurs every austral spring is projected to recover later in the century. The ozone hole is actually surprisingly not particularly, from modeling and from other studies, it's not affected by climate very much. I'll show that a little bit. And so as ODS's ozone depleting substances disappear, the ozone hole will get better. This is just a couple of plots as a function of time, and this is column amount over the Antarctic in October and over the Arctic in March. And so these are minimum values. So you can see the depletion with time here in the Arctic. You can see it in Antarctic. Every once in a while we have an odd year. This is the year with a major stratospheric warming in the southern hemisphere. I think that the main point of the variability, you can see that ozone depleting substances are causing these declines, but the meteorology and the temperature has a strong impact on the year-to-year variability of the ozone hole and the Antarctic ozone. It depends on, as I mentioned, ozone depleting substances, available chlorine and bromine. It depends on the strength of the vortex. The vortex is intact. It acts like a containment vessel that you can confine all this ozone depletion. And in Antarctica, actually, it turns out there's a saturation effect. Arctic or Antarctic ozone losses are so bad that the levels between about 14 up to 20 kilometers every year go down to 0. So it doesn't make any difference how much more chlorine you add or for a few years how much you take out. You're always going to get a pretty big ozone hole. Just to show you a series of pictures. This is from the BUV instrument in 1970, the satellite pictures of October, 1970, 71, 72, the Nimbus 7 TOMS in 79, and then these are Aura Omi here. This is EP TOMS in 2006. And you can see that the big differences over, actually this little white area is where we weren't able to take observations, but you can see that there's been a very, very strong decline. Here's the color scale over here, over Antarctica, and you get to very, very low levels over Antarctica in the last few years. Now, there was a paper, Murray Salby published a paper recently suggesting the Antarctic ozone hole is on the way to recovery. Unfortunately, whenever you publish a paper, the very next year always makes you seem a little bit foolish. Turns out that this was one of the bigger ozone holes we've had this year. So I think we probably need to restrain ourselves a little bit in declaring victory over the Antarctic ozone hole. The Arctic ozone hole, or Arctic ozone loss, I say that because there's a bit of controversy about whether we want to call this an Arctic ozone hole. This is 1971, 72, and these again are the BUV instrument. This is Nimbus 7 TOMS, and then this is from, I believe this is EP TOMS, and still, and then here's the OMI data. And you can see that over the Arctic in March of this year, again, we don't make observations here, it was very low in comparison to this huge typical mountain of ozone that we get over the Arctic. And you can see it was low in the mid-latitudes in terms of ozone. So this is March. Gloria Manny published a paper on these losses using the MLS data. And so she pointed out there were significant Arctic losses, just like the TOMS or the OMI picture showed. And on the right here, this is chlorine monoxide. This is the gas that is one of the principal catalytic components for polar ozone loss. And this is the 28th of February. This is the 29th of this year and the 26th of March this year. This is from 2010, the 29th and 26th of September. The main point being that when you have a lot of chlorine then leads to a lot of ozone loss. So if you look here, you can see very low ozone from the MLS data over the Arctic inside the Arctic vortex. You see the same thing here in the Antarctic. So I just want to say that this study really confirms our understanding. There was a little bit of controversy a couple of years about the chlorine dimer, the photolysis of this particular molecule. Maybe ozone loss would be a lot worse. But in fact, This year comes along, March 2011 comes along, and really proves that we kind of understand the chemistry and the dynamics of the stratosphere. And so this is really a confirmation of what we're seeing over the Arctic and the Antarctic. Now, the reason that you got these high chlorine levels is because it was very cold in the lower stratosphere, and that forms a lot of polar stratospheric clouds, which activates chlorine, which then leads to ozone loss. We don't understand why we had this long, sustained, cold Arctic winter in 2010, 2011. That's the mystery of March 2011. It's not the chemistry, it's the dynamics that led to these very cold temperatures. That's what's really it's kind of surprising. And just kind of as a last point, I'd just like to point out that in the assessments way back in the past, we pointed out that if you got a sustained cold Arctic winter, you would have a lot of losses. So this has in fact been known since the early 1990s, not long after the discovery of the ozone hole. So we have predicted this, and in fact it happens. And now the thing to do is to find out, well, why was it so cold? So now on to global ozone. And control of ozone depleting substance by the Montreal Protocol has protected the ozone layer, and it's projected to recover sometime in about the next 50 years. These are the ozone observations. This comes from Ann Douglas's and Vitaly Filatov's chapter. This shows northern hemisphere mid-latitude ozone levels, 35 to 60 north from 1960, almost up to the present. And there's a variety of data sets. There's a ground-based data set, and there's a few combinations of satellite data. All of these data are in excellent agreement with one another. And you wind up with something like a 4, 5, 6% depletion in the mid-latitudes. There's not really much of a depletion in the tropics. And in the southern latitudes down here between, again, 4 to 6%, again, really good agreement between these data. And here's globally, probably about a 3% depletion. This is the projections of what's going to happen in the future. This is from a whole series of models, this thick black line here that have both climate gases in it and ozone depleting substances. The dashed line up here are model simulations in which the ozone depleting substances were virtually zero. They were fixed to 1960 levels. Okay? So this is the world you have and will be projected into the future. This is the world if we never had CFCs in our atmosphere up here. So you can see there's a big difference between these two simulations. Now, this is normalized to 1960 at zero, and I put the 1980 line here to show when we get back to 1980 levels. So you can see that by about, again, fully coupled chemistry climate models. Oh, and I didn't mention that the little dotted line here is the smoothed observations. The gray bars here is models. It's the uncertainty amongst all the models. So it's not really an uncertainty. It's the differences between all of the model projections. So you get to recovery in about 2032. And again, I mentioned that the dashed line is the no ozone depleting substance. One of the really interesting things you notice here, though, is as you go over from the 1960 level, that eventually ozone rises above that level. Okay? So climate is having the impact of increasing ozone globally in our atmosphere. Okay. Let me talk a bit about increased UV, and I've gone through this a couple of times. Global UV levels didn't really increase significantly. If there were no Montreal Protocol, surface UV levels would have been very large. And in the future, cloudiness and other things are really going to be the controlling factor of ultraviolet radiation. Now, what I'm going to show you is a model simulation of what would happen if we just kept increasing CFCs by 3% per year. Now, this is two different model runs from the model. I talked a little bit about this fixed chlorine. What we do is we fix the chlorine. This is for the green line shows 1970, so it's very, very low ozone depleting substances. The blue line shows when we've increased ozone depleting substances just a little bit. Okay, and these produce. You can see this latitude total ozone here. See a little low over the Antarctic. You can see low over the tropics. Very high. This is an annual average, by the way. Now. So that's for the green line has a total of 1.2 parts per billion in the atmosphere of chlorine. This 1970 run has 1.5 parts per billion. Now, as you start increasing the amounts, which we did, you can see what happens to ozone. Little bit of depletion in the tropics, a lot of depletion in the higher latitudes. Now, the difference between the black line, that's 5.6 parts per billion of chlorine in the atmosphere, total chlorine, and the blue one is about 4.1. Now, if you keep cranking up the chlorine, it goes up to 11.5 parts per billion in the year 2020 here, and you can see ozone has gone down more. Again, these are annual averages, so you really don't see the depth of the ozone hole here, but you see its impact. If you go to 2040, it's even worse, 22 parts per billion. And if you go to 2065, you're up here to 45.6 parts per billion, and you're now down with an ozone average of about 100 Dobson units. So you've dropped from about somewhere up here in the 300s down to 100. 2/3 of the ozone layer is gone. Now this scenario here that we have, this is a 3% per year growth of chlorine. That's not particularly fast. In the early 1970s, it was going up at 9% or so. So this is a fairly modest growth rate, and shows that, yeah, if, as Mario Molina and Sherry Rowland said, if you keep cranking up chlorine, CFCs in our atmosphere, eventually you destroy the ozone layer. So CFCs from this model were an existential threat to the ozone layer. The Montreal Protocol stopped that. Now this is just UV radiation, what would happen to UV in that particular simulation. And this is the UV index. I think everybody's familiar with the UV index. For a person like me, a light-skinned person, a UV index of about 10 would give me a perceptible sunburn in about 20 minutes. Okay? These are midsummer levels, by the way. So you can see by this year, out here in about 2011, that you've gone from a value of about 10 to somewhat short of a value of 12 in midsummer. So if you just kept cranking up CFCs, you'd gone up maybe 20% by this time, 15 to 20% in the UV index. And if you kept letting it go, by the time you get out here, you're around a UV index of 30 or so. So this is the latitude of San Francisco, Washington, D.C. We would have had some really extreme UV radiation by the end by this world of 45 parts per billion of chlorine. So again, unabated emissions would have led to very, very large UV levels. I should also parenthetically add that, of course, what happens in this world is that your crop yields are going to go down. The UV radiation is going to damage crops. And in fact, in a world that we live in where we're on the edge of feeding the entire planet, if your crop yields go down 10, 20, 30%, it would have enormous impact across the world in terms of food security. I think most of you are familiar with that whenever crop prices go up, there are riots around the world. People start starving and there are riots. So the impact of this world would have been bad for things like skin cancer, but I think in terms of food security, it would have been much worse. Okay, so I talked a little bit about ozone and climate. Let me get into that in particular. Increasing CO2, methane, and N2O, okay, are going to change the ozone layer. Okay? As ODS has declined, the climate gases are going to become the most important gases for controlling ozone. This is a model simulation that Rich Stolarski did. First I should point out that our observations right now show there's been a decline of temperature in the upper stratosphere of about 4 to 6 Kelvin. And a couple chemistry climate models, these actually can simulate this fairly reasonably. Now, the plot that you see here, you can see this is the upper stratosphere, 45 kilometers. This is the lower stratosphere, 20 kilometers, 50 millibars. And these are the regression, the little thin black lines on here are the actual model data. And then the red line shows the fit to CO2, the blue line shows the fit to chlorine. We call it, it's a combination chlorine and bromine called EESC. And the yellow line is the fit to methane. All right? And you can see that when you do that fit, that's this black line, you get a really great fit. Most of it, you can see that the CFCs are going away, so most of the decline that you see here in temperature is due to CO2. There's just a more modest, you can see there's a difference in temperature scale here. These are 4-degree increments, these are only 1. So the decline of temperature in the lower stratosphere is much more modest. Okay, another thing about climate. The Brewer-Dobson circulation, that is the rising circulation in the tropics, is going to accelerate. This is a simulation from the Canadian Middle Atmosphere model showing the upward mass flux in their model. And you can see from 1960 to 2100 almost a linear increase in this upward mass flux. Okay, now, every coupled chemistry climate model that we have actually produces this effect. Unfortunately, they do it for different reasons. So it's a little bit of a mystery right now of what's going on, and observations aren't able to confirm this. So this is something that we expect to see, but it has implications for ozone. This is a simulation from Feng Li. This shows temperature on the left from the South Pole to the north, from 500 millibars up to 1 millibar. And this shows ozone in the middle here. So temperatures cool and ozone goes down, or excuse me, temperatures go down, ozone goes up. You slow down, by cooling things off, you slow down the catalytic reactions. And the Brewer-Dobson circulation has an effect down here in the bottom. So you can see ozone increasing. The Brewer-Dobson circulation, the rising motion actually reduces ozone in the lower stratosphere here in the tropics, and it increases ozone in the extratropics. Now you can add up both this lower stratosphere and the upper stratosphere there, and that's what these lines are here. So the blue line here is a sum of the ozone down here, and the red line is the sum of the ozone up here. You can see that because of CO2, ozone goes up, and that's fairly flat for all the way from pole to pole. So about the same, about 5 Dobson units between 2065 and 1980. But the Brewer-Dobson circulation change, it lowers ozone in the tropics and increases it in the extratropics. The black line shows the total change of ozone. So that's what I say there. So the main point here is because of greenhouse gases, the ozone layer will not return to its pre-industrial levels. So you can't go home again. All right. The Antarctic ozone hole has changed southern climate, and I'll go through this fast. This is the first slide I'll show you. This is a plot that shows the transition from the winter circulation to the summer circulation, the breakdown of the polar vortex. So it's a function of time, and you can see the polar vortex is breaking down much later than it did back here in the 1960s and 70s. And this is because of the Antarctic ozone hole. The Antarctic ozone hole absorbs shortwave radiation, and so as you deplete ozone, it will cool off. You delay the onset of summer. These are changes over Antarctica, surface temperature changes. In the interior here, things have cooled off. Out here on the Antarctic Peninsula, things have warmed up. And in fact, they say that the collapse of the Larsen B ice shelf is partially due to the warming temperatures you have out here on the Antarctic Peninsula, which would then be a result partially of the Antarctic ozone hole. This is a plot from this paper by Kang that appeared in Science earlier this year. This shows actually temperature changes on the left side for the summer. So there's a cooling here. And that leads to a change in the wind pattern. This is a shift of the jet slightly to the south. So you're accelerating winds down here at the surface. So you get a cooling here. You get a displacement of the jet because of the ozone hole. And because you increase the wind slightly down at the surface, that increases the wind stress at the surface on the ocean. So you accelerate the Antarctic circumpolar current, and you actually increase the upwelling south of this increase, which then brings really CO2 rich up to the surface. So the Antarctic ozone hole is actually modifying the carbon dioxide sources and sinks in the southern hemisphere. Okay, so this brings me to my summary. The Montreal Protocol has really been a marvelous success in stopping ozone depletion. We see that ozone depleting substances, both chlorine compounds and bromine compounds, are declining. There's some evidence that ozone is improving. I didn't mention one study by Yang et al. That shows that ozone is starting to come up a little bit in the upper stratosphere. The extreme UV levels that were projected didn't happen because of the Montreal Protocol. So when you hear people say, well, we didn't get these really bad UV levels, well, that's because the Montreal Protocol worked. Climate forcing by ODSs, I think this is sort of a neglected point, but the regulation of CFCs and the regulation of HCFCs has had a huge impact on climate forcing and to the benefit of the Kyoto Agreement. And finally, climate change and ozone depletion are really tied together. We've always thought that when you depleted ozone, you got more UV at the surface, and that was the principal effect. But now we recognize that, in fact, you have a climate impact of ozone depletion also. So with that, thank you for your time.
We have time for some questions. We have microphones in various places. So, please use the microphones. Yes. Okay. Very hard for me to see with the spotlights on. Yes. Could you use the microphone, please?
So, Paul, you mentioned that the cold Arctic stratosphere this past March was not predictable. So I take it was not greenhouse cooling of the stratosphere that led to that cooling?
Yeah, that's a good question. You can do the radiative calculations to see if that, in fact, could, you increase CO2, methane, N2O, everything, and then calculate radiatively what could happen. And that's just not enough. We do recognize that the amount of wave energy propagating in the stratosphere, the EP flux, was actually suppressed in the January, February, March period. And so we know that it's somehow connected with this suppression of upward wave energy into the stratosphere. So this year, in contrast, most years in the Arctic, you have a lot of wave energy propagating in the stratosphere. These stratospheric sudden warmings are occurring, and you increase ozone a lot because you drive this Brewer-Dobson circulation. This year actually lacked much in the way of wave effects. And so it stayed cooler. So actually I think the question that I think we're actually approaching is not really what caused the colder temperatures, but what suppressed all of these waves in this January, February, March period. That's kind of where the question has now evolved to. And I know there's some modeling studies going on, but I think you just have to stay tuned for answers to that.
Questions?
Hi, Paul. I may have missed it, and I understand that the HFCs are not ozone-depleting substances, but I missed any information on their climate impact. You said that they will have an impact on, I guess, temperature.
Yeah, I showed the one slide I showed the CO2 equivalent of HFCs. So there is you can actually calculate a radiative forcing effect, but I think HFCs, as I showed in that one slide that showed the impact of climate gases accelerating the Brewer-Dobson circulation, so decreasing ozone in the tropics, increasing it in the extratropics, the HFCs will contribute to that Brewer-Dobson circulation change. So even though they have no ozone depletion potential, they will modify the stratosphere through these circulation changes. So the question is, well, do they actually cause ozone depletion? The answer is no. Will they actually modify the stratosphere? The answer is yes. So HFCs kind of have a funny effect there. And you don't really capture it with these calculations of ozone depletion potentials. Chuck?
Regarding your carbon tetrachloride mystery, doesn't the high variability of the bottom-up emissions suggest that it's the reporting that's the problem?
Well, it depends if you ask the reporters. The answer to that, Chuck, is that I've been on the receiving end of a huge raft of emails from these guys actually talking about their reported carbon tet emissions. And email after email after email from different countries say, oh, we're doing ours right. And so the answer is it's entirely possible. I think people are trying to resolve that. With other gases, we don't have that problem. So it really is kind of a mystery. I mean, why would they be cheating on carbon tet and then telling the truth about, methyl bromide? And so it really is kind of a mystery.
Any more questions? Well, I'd like to join me in thanking Paul very much for a great talk. Thank you, sir. Enjoyed that.